Where's
So
Kelly?
Kelly has actually done interviews on this. Not to put her on the spot, but maybe you can tell us a little bit how students actually use this slider.
Well, actually, the sim opens up with the graph view open, and basically students don't spend a lot of time playing with these. What they do is they click down the molecules, they kind of look, and they're like, huh, okay. And then they click another one and like, huh, okay. And that's pretty much what they do.
And these are general chemistry students?
And then what?
These are general chemistry students?
These were general chemistry students in the first semester.
Yeah.
So they haven't had formal college instruction on acid-base chemistry, although a lot of them have had chemistry in high school.
Yeah.
So they have a little bit of familiarity with acid-base concepts.
I'm really surprised about this.
So, well, go ahead.
Well, did you want to get into interview stuff? Because I have a couple of slides on that.
Yeah. So Kelly actually has interviewed. I was going to make one more point, which is that Noah did something interesting with this slider. Is he said, well, there's weak, then there's this kind of transition region, and then there's this other region. In general, what we see students do when they do use the slider, I keep forgetting that I have to put it back to custom. They go, that's weak, that's strong. Weak, strong, weak, strong, weak, strong. So not to belittle students, but they examine extreme cases. Right?
Yeah.
And all this interesting stuff in the middle just kind of gets missed.
Well, unless you had an activity that capitalized.
Right. I mean, this.
Right, but the point is that we want to build into, as much as we can, into the tool productive constraints and affordances that lead to.
Can you slow down how fast people can move that thing? You can
That would
strain
not be good.
What about making
It's an interesting idea, but people really react badly to controls constraining themselves.
Oh, yeah.
What about a radio button set that slider would just be a display and you choose from like 5 choices?
You mean?
Well, that's like the pull-down menu.
Like
that's
this?
the pull-down menu. On the old one, that's the pull-down menu.
Yeah. So anyway, okay, so you guys have had lots of good comments, and whoops, what do you need? Sorry.
Oh, well,
Do you want
so,
new or old?
Sorry,
I've been talking. Maybe I have to flip over the student or...
Okay. Yeah.
I mean, I'll say I really like the macroscopic or the microscope or the magnifying glass view of the molecules much better in the new one than the representation of the ions in the old one.
Yeah.
Bigger dots.
The dots are not as meaningful, and I think it's much easier to see kind of the shapes and colors and stuff.
Yeah.
The idea of the microscope,
So, you know,
or
one of
the
the
magnifying glass is
things,
good too.
one of the things in terms of complexity that we probably won't be able to get to, but is this notion that concrete representations are, in general, inherently less complex to make sense of. And so we, in the new sim, that's part of why we start with spheres rather than graphs. And something that was found in interviews also was that even though the first tab of the old version with all the graphs and everything was kind of overwhelming initially, once students played around with the dots in the beaker, that actually was much more intuitive, and they made sense of what was going on from that. So that was part of our design choice to start there.
Yeah.
Right.
So,
just to give, I guess, a little bit of maybe evidence. So what we did with this before acid sim was I did 8 interviews with students in general chemistry, and what I did was I started out the sim in different states. So in one state, it was just like you saw it had the graphs up to begin with, and then for the other 4 interviews, we closed the graph, and all they had was this sort of particles in a beaker. And I wanted to see if that would affect how they engaged with the sim, if they learned anything different, if, what they did. So like Noah already hinted at, like, after the first initial response, there really wasn't much difference, because you can do whatever, you can close things, you can open things in both setups. So it was just what they saw initially, but the reaction when they first saw the sim was drastically different based on if the graph was up or if it was something in a beaker. So I have a short clip of a student.
Go to, there.
So this is a student who saw the graph view first. So what we consider to be the more abstract or more complex, you could think. And watch her body language too.
Okay. And you can open it if you click on that screen capture button.
second tab. Kind of looks around. Goes to the third tab, looks around.
Okay. This part is pretty clear. Right here is just like a lot of things at once.
Just like a lot of stuff. She didn't want to touch the mouse. And like the next thing she does is she turns off the graph.
Okay. And you can open it at the bottom.
Oh, that was
Wow. So, you know, you can't help but wonder, well, the interaction of her feeling like she's supposed to know something, like for fear of clicking on something stupid because she doesn't know chemistry.
Actually, we try to set up the interview so that they feel pretty comfortable. They know they're not really supposed to know everything. We say, we just want you to think aloud, play with everything, tell us what you're thinking. So we try to get around that. But
So with respect to that, that may actually be what's going on, but the fact is that we actually pretty rarely see that in interviews with vet sims. Even when we show a student a simulation, say just play around and see what you can figure out and talk out loud and go. We very rarely see students kind of set back like that. So it may be that she got into this mode of thinking, oh, this is chemistry, I don't want to mess anything up. But what we think is that it's actually something inherent to this simulation that's causing that.
That has triggered that.
Yeah. When I first looked at it, I was like, oh crap, I don't know any chemistry. Like, that's the first thing I thought when I looked at that one.
So,
Wow.
I also really appreciate it in the new introduction tab. It's definitely, it's a much less intimidating interface, and you do feel like you can explore. There's not much to do, but you can sort of figure out what the representation means. I guess what we were maybe stressing about a little bit was, why not have a tab in the new one that allows you to do some of the things that the old one, I mean, you know, this is part of the idea of the tabs, is that you can move to once you understand something, you can move to some more complex. So for instance, this, having that graph side by side with the little molecular representation, at some point that becomes useful. If you're really trying to learn how to interpret that graph, I find it helpful to be able to see it side by side with the picture. And I'm wondering if that's your learning goal in a college level chemistry class, having that available, you know, it's like it should definitely not be there when you first started up because it is intimidating. I'm just wondering why you completely eliminated it.
There's some discussion about making some modifications to the old one based on what we know and posting that.
Well, you notice that it's been rechristened as advanced acid-base.
Right.
I mean, there's a decision point. At what point do you stop adding tabs and you just consider it to be a new simulation?
You can do that.
That's kind of the idea. That's sort of the implication of
the college kids.
Okay, so we've got about 20 minutes and we have like 30 more slides. So no, I'm just kidding. But we do have some more stuff to tell you guys, and we have a little bit of theory that we'd like to get into as much as we can in 20 minutes.
okay, so I'll kind of do something that's not theoretical, so we can set up the stage for Noah. So also what I did was, because I saw that students were having these, weren't engaging with the acid-base sim as we thought they would, because a lot of experts said, oh, this is great, we really like that the equations expand and contract when you change the strength slider, and actually overheard a TA say, oh, this is really cool. So actually what I did was I interviewed TAs that were in this, the TAs of those students that I interviewed before. So these were Gen Chem TAs, had them play with the sim just like we have the students. And when it got to the equation part, I had very different reactions based on like the students in the class versus their TAs. So the student would open up the graph view and see it expand and be like, whoa, okay, not sure what that did. I'm confused why these got bigger. Maybe it's trying to, I'll have to go back to this later, but then they wouldn't go back to it. Whereas the TA, when they saw it, they're like, oh, I think this is really good. You know, I think seeing the equations and having them change as you change concentration helps because it takes students a long time to equate that with anything. So it's kind of like we have this, experts kind of look at the sims in a different way than students, and that's why it's always really good to get student feedback because what we think is great may not actually work and be overwhelming. So that kind of leads into a little bit of the theory, I think, of trying to quantify complexity.
Okay. So we've seen this actually lots of times where experts look at a sim and think that it will make lots of sense to students when it doesn't. And we've also seen vice versa, where experts have looked at a sim and not understood what they're looking at, where students open the simulation, make sense of what they're seeing right away. And usually it's because we're using non-standard representations in the simulation that make sense to students that experts actually aren't used to looking at.
Give an example for that?
Yeah. My favorite example is nuclear decay, alpha decay. I'm not going to bring it up, but basically when you look at a decay curve, you expect to see an exponential decay. And in that simulation, what you actually see is little alpha particles flying across, and then when they decay, they fall down. And what ends up happening after a while is they kind of pile up on one side, and you get a whole bunch piled up on the left side of the half-life time, and fewer on the right side. And the experts that we showed it to said, "What's going on? Why are they falling down?" And stuff like that. And students would look at that, and after playing with it, they'd be like, "Oh, I see. There's a whole bunch more on the left side of the half-life than the right. Actually, there's not a whole bunch more. It's about even. But they would recognize what was going on, that the half-life was about in the middle." So, I've shown some of this to you all before, but essentially we've tried to come up with this model where this is supposed to be a generic simulation with, say, a concrete-ish kind of representation, maybe like pictures of molecules, and abstract-ish representations like bar charts or something like that. And what we've been thinking is that a lot of playing with a simulation and understanding the underlying concepts is about identifying and making sense of cause-effect relationships. So one way of getting at this is to create this matrix that has what we call causes on the left and effects on the right. So causes would be like moving the controls over there that would change things, and effects would be how the readouts change. And then what we do is we put in, right now, the first order, or even zeroth order, is to put a 1 if a cause has an effect, and a 0 if a cause doesn't have an effect. Yes?
Do you mind interrupting?
Not a problem.
Is this based on the programmers or based on the students? Which is to say, if students don't see the cause and effect, does it not exist?
This is based on the sim.
So the program.
This is a way of analyzing the
how complex the sim is, not how complex people see it. Okay, great.
Yes, exactly. We'll get into that.
Yeah. Well, this is like your textbook analysis. Okay, gotcha.
I think so. So now, this is a theory of looking at a sim sort of face validity in a way, saying let's look at the sim and see what we think what things cause effects, whether or not you recognize them or not. So yes, you could do this if you had a sophisticated algorithm. It could spit it out from the code. Now the idea is that suppose readout 1 and readout 2, this big star and this red bar right here were related to each other. So that when you change, say, control 1, it made this bigger and smaller along with the red bar. Well, then you could associate those two with each other, and you could actually blend them or combine them together into one idea, and that might be represented by, let's call it readout 1, 2, where now you think about both of these as sort of the same idea.